In this lesson, we will explore how to apply sinusoidal functions to model and solve real-world problems. Now, with that, we're going to bring together and remember all the different transformations that can occur because we have to interpret graphs and decide what is our A value, or K value, D value, and C value. So some key tips when we're investigating application of sinusoidal functions. The following information will help you determine the values of A, K, D, and C in the function. So looking at the possibilities of different transformations, A, we know is that vertical stretch or compression, but it's the amplitude. So to calculate the amplitude, we take the maximum value minus the minimum value and divide that by 2. The equation of axes, again, is the maximum value plus the minimum value divided by 2. If the graph is reflected into the x-axis, A is assigned a negative sign. So keep that in mind. The period is always 360 divided by K. The horizontal translation or the phase shift, check for the shift from the graph of sine of x and cos of x. So when we're looking at cosine, you want to see how far has the graph moved from the y-axis to its maximum. And that uh, x value represents that phase shift, left to right. With the sine function, we want to see how far from the y-axis has the function moved to the equation of axes. And again, at that x value represents a d. So each graph can be defined as a sine function, the cosine function. There's multiple equations we can use with different d values. So there's multiple answers. Just a little note, it is often easier to transform the function y equals cosine x than y cosine of x because in many graphs it is easier to identify the coordinates of the peak, the maximum of the function. Usually the horizontal translation is the x coordinate of any maximum. So due to their periodic nature, we can both describe a sinusoidal graph in terms of sine and cosine and use their phase shifts to describe one in terms of the other. Okay, so when you're looking at sine, that horizontal translation or phase shift, the phase shift for sine is equal to the phase shift for cos minus 90 degrees over k. Same thing with cos. You can take the phase shift for sine plus 90 over k. Okay, so let's determine an equation. So we're given the following graph, and we want to express it in terms of the cosine function. So again, we want to look at the max, look at the min. That'll help us decide what the amplitude is because we can use that, the equation to decide, determining that using your max and min, and same thing with the equation of axes. So that's where we always want to start. You can often read it off the graph, but when you have that max and min, we know max is equal to 2. The min is equal to -2. So the maximum, the peak, minimum is that trough. Okay, so we know A is equal to max minus your min. So 2 minus -2, divide that by 2. So A is going to equal 2. 2 plus 2, 4 divided by 2, which is 2. C is going to be max plus my min. I don't think I have to write it out. We'll just use the numbers. 2 plus -2, and we're going to divide that by 2. So C is equal to 0. And as we can see off the graph, we could have easily said A is equal to 2 when we know that equation of axes is y equals 0. Okay, so when does one full cycle occur? Again, it's always best to go from max to max or min to min. So let's take it from this min to this min. So that's when one full cycle. Okay, so then the period is always the difference, which would be 300 minus 60. So the period in this case of one full cycle occurs at 240 degrees. Okay, you're reading it right off the graph, and that always helps us determine the K value because the K value, so K is always 360 divided by your period. So then K is equal to 360 divided by 240. So then k is equal to 1.5, or 3 over 2, k is equal to 1.5. Okay, so with that in mind, then we just need a d-value. Now, again, it's asked us to use the cosine function. So again, the d-value can be different depending on where you want to take it. We can go negative d. So in this case, d is equal to negative 60 degrees. Okay, we can also, and that would be a equals positive. We can also do d is equal to positive 60, but a would have to be negative. Or we can say d went all the way over here, so d is equal to 180. All of these would provide us an equation that represents the following graph. Okay, so if we decide d is equal to 60 degrees, that means a has to be negative. If a is negative 2, therefore we can say f at x is going to equal to negative 2 cos k, which is 1.5 x minus 60, and then it's plus 0, so we don't have to put in the plus 0. Okay, so therefore we can also say if d is equal to, say, 180, if a is positive 2, therefore we would have f at x is equal to positive 2 cos k is still 1.5, just be x minus 180 degrees. And then we could have added another one. We could have said if a is positive, but you wanted to go to the left. So we can say, let's throw that in there. So d is equal to negative 60 if a is equal to positive 2. We can say f at x is equal to 2 cos 1.5 x plus 60. And again, there's no c value. Okay, so as you can tell, and we can keep going, but we don't need to show all three. We just have to show one. But I just wanted to show you that there's many, many, many options. All right, now let's look at the exact same graph, and this time for the sine function. So we already know a and c would be the same, so we don't have to show the calculations. A is equal to 2, c is equal to 0, k is equal to 1.5. So those don't change. The only difference will be what our, again, our d values would be if we're using the sine function. So if you notice with how the graph is, it actually at 0, we're at 0. The only difference is for sine, it should be going up to the maximum. But because it is reflected into the x-axis going down to the minimum, so if we say a is negative, there is no d value. So we can say d is equal to 0 if a is negative 2. Therefore, the graph equation would be f at x is equal to negative 2 sine 1.5 x. Okay, however, if we want a to be positive, then we would note that that horizontal translation would go to d equals 120 degrees. For sine, I did sine in red, so it's a little bit different than the green. And that means that d would equal to 120 if a is equal to positive. And that's for sine. Okay, so green, I'm going to just make a note. Red is sine x, and green equals cos x. Let's keep that in mind. So we'll go back to again, if you wanted d is going to equal to 120 degrees if a is positive 2. So therefore the equation would be f at x is equal to 2 sine 1.5 x minus 120 degrees. Okay, so lots of options. We could have gone to the left as well. We don't have to show all those options, but we know we have something. Okay, whew. We have Betty is swinging back and forth on a trapeze. Her distance from a vertical support beam in terms of time can be modeled by a sinusoidal function. At 1 second, she is the maximum distance from the beam, 12 meters. At 3 seconds, she is the minimum distance from the beam, which is 4 meters. Determine an equation of a sinusoidal function that describes Betty's distance from the vertical beam in relation to time. Okay, so lots going on. So if we did, I'm going to do a quick little sketch because I'm more a person that needs to see that visual. So let's see, we have, we know that, okay, so we know that, I'm going to highlight what we have. Her distance from Rome in terms of can be modeled at 1 second, she is 12 meters away. At 3 seconds, she's at the minimum, that was at the maximum, minimum at 4 meters. Okay, so let's get that little visual. At 1 second, she's at her maximum. So let's do 0, 1, 2, 3, 4, 5, 6, 9. Okay, so this is going to be time in seconds. Okay, and our height is in meters, and we'll go up by, say, twos. Which is a quick sketch. Okay, and this is our height. The distance. Okay. Okay, so we know that after 1 second, she's at her maximum, which is at 12. Okay, and then at 3 seconds, she's at her minimum, which is at 4. Okay, so we know if it takes her 2 seconds to get from max to min, that means she has to go back to the max, and that's going to take her another 2 seconds. So that helps us with the period. It takes 2 seconds to go from max to min, but that's not the full cycle because she has to come back to the max in order for it to be a complete cycle. So 2 seconds later, so at 5, she would be back at her max. Okay, so halfway between that, so for max is 12, min is equal to 4, halfway between that. So it looks like every second she is then back at her, she's doing a movement. So back halfway between, if we took 12 plus 4, which is 16, divide that by 2, she's at 8. So then at 8, 2 seconds later, she's at 8. 1 second later, she's back at 8. So that equation of axes would be such. Okay, so max. And then she would continue. Okay, so keep that in mind. Now, we're going to do our calculations because we know the max and the min. The period was the big thing. So period, it took her 3 minus 1 seconds to get from max to min, but that's not a full cycle. So half a period, so full period, you double that. Is 2 times 2, which is 4 seconds. So the period is 4, because again, we need that in order to come up with our K value. Okay, so again, we know our max, we already said it was 12, our min was 4, so let's go about and figure out the rest of the information for our equation. So we know A is always, absolute value of A is max minus our min, so 12 minus our min, which is 4. Let's divide that by 2. So A is equal to 8 divided by 2, which is 4. C is going to be max plus or min, so 12 plus 4, divide that by 2. C is going to be 8, which we have that. Excellent. Now, because we start our equation of axes, that means that we should probably use the sine function, right? Because you're starting at the equation of axes. We are still missing one different property, which is again our K value. So our K is always 360 divided by our period. So K is going to equal to 360 divided by 4. So K is equal to, so 360 divided by 4, which is going to be 90 degrees. Okay, so given D at T, we're going to say is equal to 4 sine, we started an equation of axes, so K value is 90 plus 8. Okay, however, if we wanted to use, and that's when A is positive, correct? So we can say when A is positive, we have to have a D value. So when A is positive, that means we didn't go to our max, so that means D is equal to 0. Okay. However, if we wanted to say A is equal to negative, so in our case, -4. If it's a -4, I should put that 4. If we wanted to say that A is -4, then we would look on our graph, our little sketch, -4, and we see how far, and look that it's going down to the minimum 4, and that's at D equals 2. Okay, so we can say D is equal to 2. So, or we can say D at T is equal to 4 sine 90 T minus 2 plus 8. Okay, but what happens if we're going to use cosine? Now remember, cosine always starts at its maximum, and these refer again for sine. This is for sine. If we wanted to use cosine, it doesn't matter, I'm just giving you lots of options. So if we wanted to use cosine, we want to see up here where or how far as it moved from the y-axis. It would be D is equal to 1 if A is equal to positive 4. And this is for cosine. Now, if you were to put all these equations into decimal, you'd get the exact same graph. Okay, so keep that in mind. So I'm just giving you lots of options. We're going to say for cosine, if we wanted to say A is equal to positive 4, then D is equal to 1. So we can say D at T is equal to 4 cos 90. We're going to say T minus 1 and then plus 8. Okay. If, however, we wanted A to be negative, so we want it to be negative, we're going to say A is equal to -4, D is going to equal to 3. And again, this is for cosine. Just to give you options. And again, we don't need to show all these different options on the assessment, but it's good to know that we have different ways of expressing the same graph, and it's all based on that D value. So we said if it's -4, okay, -4 cos 90 T minus 3 degrees plus 8. Oh, what? I'm not sure why I put degrees there. Okay, excellent. Looking at example 3, we have a ship is docked in port and rises and falls with the waves. The equation of the sinusoidal function is given. D at t is equal to 2 sine 30 degrees t plus 5. Models the depth of the propeller d at t in meters at t seconds. So what I wanted to do actually is the t on the outside. Okay, so with that in mind, we want to identify the A, K, D, and C and give ourselves a good sketch. A visual is always a good idea. So we know A is equal to 2, K is equal to 30, D is equal to 0, and C is equal to 5. Okay, so again, it is a sine function, so the parent function key points for y is equal to sine of x. At 0, we're at 0. At 90 degrees, we're at 1. At 180 degrees, we're back at 0. 270 degrees, we're at -1. And then 360, we're back at 0. Okay, using mapping notation, we're going to have x over k, which is 30, plus my d, which is nothing. So we're going to put 0 to y plus 5. Okay, so substituting the different values of x, 0 divided by 30 is just simply 0. 90 divided by 30, which is simply 3. 180 divided by 30, which is 6. 270 is 9. And then 360 is 12. Substituting y, 2 times y. 0 plus 5 is 5. 2 times 1 is 2 plus 5 is 7. It's going to be 5. -1 times 2 is -2 plus 5 is 3. And back to 5. Okay, so plotting that, we'd have 2, 6, 8, 10. And we know that's going to be d at t. Okay, and then we have, we're going, the scale is all the way up to 12. So I think going up by ones would work. So we'll just label every other. So 2, 4, 6, 8, 10, 12. So this is the depth of propeller, which is in meters. And this is the time in seconds. Okay, so at 0, we're at 0. Sorry. At 0, we're at 5. At 3, we're at 7. At 6, we're back at 5. At 9, we're back at 3. And then we're at 12. We're back at 5. So like such. That's one full cycle. Okay? All that t. So I have, what is the period of the function and what does it represent? So the period, again, is equal to 360 divided by k. K we know is 30. So if we took 360, divide that by 30, k is equal to 12. So the period is 12. And we can read that right off the graph. It took 12 seconds for one full cycle to occur. So therefore, the period is 12 seconds. And it represents the time it takes for the ship to complete one full up and down cycle with the waves. Okay. If there are no waves, what would be the depth of the propeller? Okay, so if we looked at if there was a waves, if there are no waves, with the depth of the propeller would be, that equation of axes would be 5 meters on the surface of the water, which is that equation of axes. Okay, what is the depth of the propeller at 6 seconds? So what we're trying to figure out is what d at 6 would be. So we just substitute that right into the equation. So we know that it would be 2 sine 30 degrees times 6 plus 5. And always following bet math. So d at 6 is equal to 2 sine 30 times 6, which is 180 degrees, plus 5. 2 times sine of 180 is actually 0, plus 5. So d at 6 is equal to 5. And again, we could have read that right off the graph. So if we look here, the equation of axes, d at t is equal to 5. So therefore, answering that, the depth of the propeller, the depth of the propeller at 6 seconds is 5 meters. Okay, what is the range of the function? So we see the max, we see the min. Okay, so we know, and I'm going to just state it, max down here is 7, min is 3. Therefore, the range of the function is d at t is an element of real. However, d at t has to be greater than 3, but less than or equal to 7. Okay. Okay. Within the first 24 seconds, at what time is the propeller at the depth of 6 meters? So if we read that off the graph, oops. Okay, so when is it at 6 meters? So if we look on the graph, 6 meters is such at this point. When t is equal to 1, 6 meters is here. When t is equal to 5, okay, and then we have, when will that happen again? Well, if we took those 2 points, and we have to make sure we're coming 24 seconds. We've only done 12 seconds, so 24 seconds would be double that. We know that the period itself is 12. So if we start at t equals 1, if we add 12, that would be the second point when the propeller is at a depth of 6 meters. Likewise, with 5, we would add 12, and that would be the other point where the propeller is at 6 meters. So we're going to show you that at T1, which is equal to 1 second, and then at T2, it was also at 5 seconds. Okay, so those are the 2 times at which, okay, so all we're going to do, we're going to add the period of 12 seconds plus the period 12 seconds. So that means third time at which it would be 1 plus 12, which would be 13 seconds. And the fourth would be 12 plus 5, which is 17 seconds. Now it asks for the first 24 seconds. If you're not sure, if you try to add another 12 plus period of 12 seconds, you would be at 25 seconds. And again, that would be beyond what they are asking. Okay, so don't forget a therefore statement. Therefore, the propeller is at a depth of 24 seconds at 1 second, 5 second, 13 seconds, and 17 seconds. Okay, height of the propeller at 249 seconds. Now your best bet is to put that into the equation. So we know a D at 249 would equal 2, again, 2 sine 30 times T, so 30 times 249 plus 5. Okay, so we write into the equation. So 30 times 249, so 2 sine, always following BEDMAS, which would be 7,470 degrees plus 5. 2 times sine of 7,470 degrees, which is -2 plus 5, which is equal to 3 meters. So the height of the propeller, or the depth, we can say therefore the height of the propeller, height of the propeller at 249 seconds is 3 meters.